Welcome back to RISC-V assembly. We have learned 15 assembly instructions so far, and we are just about to add a dozen. We are going to look into logical instructions in RISC-V assembly. They should be fairly familiar to us because we have seen in high-level languages like C or Java. Bitwise ANDs and ORs and XORs have their direct counterparts in the assembly language, and so do shifts left or right. They're often used for isolating a byte or a nibble out of a word, or by packing bytes or nibbles into a word for more efficient storing of data. Let's take a look at a few examples here. Logical instructions always have two variants in RISC-V. They have a register-based version and an immediate version, and that should come to no surprise to you because both of them are frequently needed and frequently used, and they're relatively inexpensive to implement in hardware. What we'll see is that they share the same data path as arithmetic instructions, so whatever we needed to implement adds and subs, we'll be using for implementing ORs, ANDs, XORs, and shifts. So in this case, let's take an example, register-based AND, bitwise AND. So we'll take the contents of a register of X6, AND it with the contents of a register X7, and store the result in the destination register X5. In its immediate counterpart, we'll take the value from the register X6, AND it with an immediate binary value that represents a 3, and store the result in the register X5. This kind of operation is used for masking, as I've said. The previous immediate instruction would isolate the least significant bits on the right and zero out everything else. In this case, and immediate with an FF hexadecimal will isolate the least significant byte. If we AND immediate with FF in the most significant byte position, we would isolate the most significant byte. Keep in mind that the instruction set is still lean in RISC-V, and we don't have unnecessary instructions. The most notable one that is missing, there is no NOT in RISC-V. Why? Because we don't need it. If we simply XOR a content of a register, a value in the register with all ones binary, then we invert every single one of those bits. Remember, this is done always for simplicity. Unnecessary things are not going to be there. Let's take a look at logical shifting. So, shift left logical comes in two forms, SLL that operates on the register contents, and the immediate that works with an immediate value. So in this case, SLLI X11, X12, 2 will take the value in the register X12, shift it to the left by 2 bit positions, and fill the 2 least significant bit positions with zeros. So if we have a hex value of 2 in the register beforehand, after shifting it by 2 to the left, we are going to end up with 8. We have essentially moved this 1, 0 to the left by 2 bit positions and inserted zeros in the least significant bit positions. So, a quick question for you. What arithmetic operation we have just executed? Think about that for a sec. We have multiplied it by 4, so 2 times 4 equals to 8. And you can think of that, this extends easily to multiplication with any power of 2. So we can easily multiply with 2 to the n. But here's a quick question for thinking about this. How do we do multiplication by 12? Well, we can shift to the right by 3, which will multiply by 8, then we multiply by 4 and add those two results. We ended up with multiplying by 12. This is, by the way, commonly done in DSP. Now, shift right logical does the opposite. Int shifts the word to the right by a given amount and fills the most significant bit positions with zeros. So that's a logical shift. When we are working with side numbers, we generally perform the arithmetic shifting. Arithmetic shifting does the same. Shift right arithmetic that exists in register and immediate forms moves n bits to the right and inserts the sign bit into the empty bits. It basically replicates that topmost bit into the empty positions that we have emptied by shifting to the right. Okay, so in this example, if x10 contained a decimal value of -25, see, notice its topmost bit is negative, so it's a negative number. If we execute shift right arithmetic immediate by 4 bit positions, the result is going to be this. We are going to be, will shift everything to the right by 4 bits and fill the topmost ones all with ones. What's the result of this? It's kind of close to a division. We took 25 and divided it by 16, and we ended up with 1 point something, minus 1 point something. There is a slight issue here. By convention, C arithmetic requires us to round toward 0 always. So in this case, the result should have been rounded towards -1, not towards -2, which is the result that we got. But you would have to fix that to implement true division. That's doable, but requires a bit of work. A few more instructions, actually. That's it for the logical instructions. We'll continue with the rest of RISC-V assembly in just a bit. See you there.